first lecture in elements and compounds, getting to know our periodic table and what's on it. All matter, as we may know, has mass, occupies space. That matter is composed of atoms. Atoms are, if you zoom in, if you go in smaller, 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 if you've got your Ant-Man suit on and you shrink, 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 before you go to quantumania, you get to atoms, tiny little pieces, building blocks that make up our world. Everything that you can hear, feel, see, experience is made up of atoms, which is mostly true. The properties of those atoms and the way that they're connected determine matter's properties. One of our definitions, there's a bunch of ways that we can define it, but we're going to define it here as the smallest identifiable unit of an element. And an element is a substance that can't be broken down into simpler substances. So if we look at the periodic table in the class, our periodic table shows us all of the elements. We've got 118 options. 91 or so of those exist most of the time. So every box on our periodic table is an element. And the smallest piece, the smallest little mote of element that you can have is an atom. If you go smaller than that, it's no longer an atom, it's something else. Atoms are also very, very small. The largest atom, so out of all of the 118 atoms, the biggest one has an approximate diameter of this tiny number. So if you have your little pinky finger, if you lined up 18 million of them, that's about how many it would take to get across your pinky finger. I think the number's more like 100,000 to get across the width of a human hair. Your mileage may vary. Depends on how thick your hair is. We got this fun picture of Democritus, and by picture, of course, I mean painting. Leucippus and Democritus, they were around a long time ago, over 2,000 years ago, something like 2,500 years ago. Democritus suggested if you divide matter, if you basically just, what if I cut something in half, and then I cut it 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 in half, and you keep going and doing that, but I don't want to. If you keep going, he said eventually you'll end up with tiny indestructible particles. That's what he believed. He called them atomos, and those mean atom, which means indivisible. So it can't be broken down any further, which is true if we're talking about elements. Much, 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 much later, more than 2,000 years later, Leucippus and Democritus got their flowers. Their ideas started to become more popular. There were other competing ideas at the time that things were made up of basically the avatar elements, not the blue people, the kid with the bald head. So people thought that the world was just made up of different elements, and if you went down far enough, you'd get like the quintessence of the elements or something. I don't know. That's obviously not true. Otherwise, I would be bald and I'd have an arrow on my head. John Dalton's atomic theory came about in the 1800s. The dates are mostly not important. The theory is much more important. So John Dalton's atomic theory has a couple of points, depending on who you look at for your history. But one of the ideas is that each element is composed of tiny indestructible particles called atoms. So those tiny little building blocks, when you cut everything down, that's the smallest piece you can get. All the atoms of a given element, so any of the boxes on the periodic table, have the same mass and other properties that make them unique. So if you take a piece of sulfur, a little sulfur atom, you take another sulfur atom, they should be identical, indistinguishable. And the atoms also combine in simple whole number ratios. So there's no fractions, there's no halves. It's 1 to 1, 1 to 2, 2 to 2, 2 to 4, 2 to 8, 2 to 7, other things like that, to form compounds. Why would they form whole number ratios and not partial number ratios? because of point 1. They can't be broken down any further. So if you can't break them down any further, you have to have whole number ratios. This is similar to if I was making student groups. I couldn't create a student group that has 2.5 people in it because I would go to jail. We do have good evidence for the atomic theory, the idea that atoms are as small as you can get for an element. They're indistinguishable from other elements of the same thing or other atoms of the same element, and they combine in simple whole number ratios. Scientists at IBM, other scientists have done similar things. They used a fancy tool called a scanning tunneling microscope, and they moved carbon monoxide molecules. And they made this stop motion video called, I think it's an atom and his boy, a boy and his atom, something like that. So it's a little stop motion picture that they made, and the film size is 45 nanometers by 25 nanometers. And nanometers are 10 to the minus 9 meters. So, and that's obviously not correct scientific notation. Maybe something like that. That many meters was one of the dimensions of the film. So it's smaller than you'd be able to see. You'd probably not be able to see it with a microscope either. The scanning tunneling microscope is a special kind of tool. It's basically a tiny little needle that they move around, and it bumps up and down when it comes into contact with things. It uses electricity. It's not important for the class. Okay, atoms are made up of parts, as it turns out. They are not indestructible. You can go smaller. Democritus and Leucippus were not correct. It's made up of 3 particles. Three subatomic particles that we'll talk about in the class. Two of those particles are the proton and the neutron. Protons and neutrons have very similar masses. So they're basically the same size. Electrons, on the other hand, have almost negligible mass. They are very small. We'll talk more about that on the next slide. The way that we measure protons, neutrons, and electrons in terms of their mass, we can measure them in terms of kilograms, but then we're talking about like 10 to the minus 27 kilograms, somewhere in that range. So it's really small numbers, and so we have a special unit that we made up just for talking about these subatomic particles, and that's the atomic mass unit. It also helps us talk about some of the elements on the periodic table. So on the periodic table, the atomic mass unit with units of AMUs, this is the unit for the number under each element. It's defined based off 1/12 of the mass of a carbon atom, and the carbon atom has 6 protons and 6 neutrons. Together, that's 12 particles. So it should be about the average mass of a proton or a neutron. And it's like rounding close. Other properties. I'm just trying to make sure that I'm talking about this in the right spot. Cool. Other properties. Our protons and our neutrons both exist inside of the nucleus. And I think this is coming up in a future chapter, but basically we'll skip it a little bit. We've got a small, densely packed core in our atoms. That's our nucleus. And then around it, sort of the effect that this pointer gives, we've got electrons. And most people probably think of electrons as flying around in little orbits, sort of like a mini solar system, really packed down. Think Jimmy Neutron, any of the intros, outros, when they're... My brain went there. Hopefully that's not dating myself. So we got these little electrons that are flying around, and we've got, we'll say that the blue one is a proton, and these red ones are the neutrons. So our protons are in the nucleus. They also have a positive mass. Pro like in favor of, pro positive. And then we also have the electrons. They were formerly called negatrons, nega like negative, and for some reason we switched it to electrons. I think negatrons, negative, makes a little more sense, but there was a reason that we switched, I'm sure. And then our neutrons, the neut part, like in neutral. So there's no charge for neutrons. I'm a little more than 50% sure that we will talk about these in more detail in other slides, but it might be next chapter. So we might be jumping the gun a chapter. Questions at this point? Cool. Another comparison between protons and electrons. The proton is it's about 2,000 times more massive than an electron. If our electron, our small particle, is a watermelon, who knows what our big particle would be? What's 2,000 times bigger than a watermelon? More mass. Who's not looking at the next slide? Not quite a train, it's a semi-truck. So if you can imagine getting hit by a watermelon, then I guess in theory, if you compressed a semi-truck down to the size of a watermelon and you got hit by that, that'd be 2,000 times the force. A watermelon will put you down, and a semi-truck will put you down in another way. Just guessing. Okay, keeping track of our subatomic particles. So we've got those 3 subatomic particles. We've got protons, neutrons, electrons. You should know all of those names. We're going to talk about protons first. They are arguably the most important, but I don't want to argue about it. We'll just say that they're important. So the number of protons in the nucleus of the atom, again, that's the tiny little core at the center of it, that number is the atomic number. So the number of protons, P+, is Z, atomic number. And this is important because the number of protons is how we define an element. So any of the boxes on the periodic table, those are defined based on the number of protons they have. You can count up the protons or determine the number of protons, and that determines what element it is. And that imparts a lot of the properties of the element. If you change the number of protons, you change the element. So for example, sulfur has a Z of 16, silicon has a Z value of 14, gold has a value of 79. If you change that number, if you bump it up, you bump it down, it changes it to a different element on the periodic table. And again, that's Z. Any clues why it might be Z? Why would we choose Z? Unless we have a German in the room, you probably are going to guess. Z comes from German for Zahl, which is number. And probably the reason that it's in German is that a lot of mid-modern chemistry was done in Germany. There were a lot of famous German chemists. I think that's just a fun connection to figure out why it's Z. Maybe that'll help you remember. If we look at the periodic table, our modern periodic table lists all of the known elements, all 118 of them, according to their atomic numbers. And we start counting from the top. And then we move over to the end of the row, and then we jump around to the start of the next row, and we count up, and we move across, and then we move to the next row, and so on and so forth all the way through. And the chunk that's cut out and usually put below the periodic table are lanthanide and actinide series. We mostly don't need to know about, but those also get inserted in there on the periodic table in the slides. It's right here. On the one in class, it's La through Lu and Ac through Lur. Right. Go. Right there. So that's where all of those fit in. Obviously, if we put them in, it would make the periodic table like unnecessarily wide. So that's why they're usually pulled out. We also have another number, the mass number. The mass number is the number of protons plus the number of neutrons. So this is the number of particles that are in our nucleus, that tightly packed, dense little core that makes up the heart of our atoms. And we can use that in combination with our Z number to figure out how many neutrons we have. So if we know our A value, our mass number, if we know our Z value, our number of protons, that can help us get our number of neutrons. Any guesses on why A might be A, what it stands for? It's also German. It is this word. So I'm guessing we probably weren't going to just guess that. It looks kind of like atomic weight. Atomgewichte is my guess at pronouncing it. Sorry to Germans. But the Wichte part at the end sort of looks like weight. There's some carryover, some crossover between English and German, the way that words are put together. So A for basically atomic weight. And since protons and neutrons are both massive, they're big. They're the semi-trucks versus the watermelon. They're the semi-trucks, they're the big ones. Those are the ones that we count for the atomic weight. The electrons don't really matter for mass. We also have symbols. So each of our elements gets represented by a unique chemical symbol. They're either 1 or 2 letter abbreviations. Some of them are based on English, which is great. Several of them are based on the Latin or Greek. So if you speak a language other than English, there's a chance that you might have better access to those. Some other languages also use those as the actual name for the element, I think. An important note for our symbols is that the first letter of the symbol is always capitalized. And it's only the first letter. So these are sort of like state codes, like CA, AL, AK, AZ, except only the first letter is capitalized. That way we can differentiate between our 2-letter codes and our 1-letter codes. Unlike our state codes, of course, there are 118 options. You don't have to know all of them if you're going to prioritize some. I would say focus on the top maybe 4 or 5 rows. Those are going to be the most important. Don't worry really about the lanthanides and actinides, the ones that we pull out. Don't worry about that very last row in the continuous upper block. Focus more on the stuff that's in the first 2 columns, the last 6 columns, and then maybe the first 2 rows in between, 2 or 3 rows. There is a quiz on Canvas that can help you with practicing these. I think it's posted, so you can go in. It doesn't cost any points. You just go in, you play the game, you click the correct symbols. For our first exam, you get the periodic table that has names on it, but I think I take those away for the second and later exams. So you don't have to have them down now, but it's a good thing to have for later. It's a fun little thing that you can practice when you've got some free time. A couple of examples of modern versus historical names in English. Potassium, sodium are kalium and natrium. So the symbol K for potassium comes from kalium. The symbol for sodium, Na, comes from the historical name natrium. And other examples below. There's 2 that I've got memory devices for. Lead, which is a metal, kind of a thick metal, not particularly hard, relatively soft. Those are the same thing. It has the symbol Pb. What else is thick? Peanut butter, Peanut butter is thick and creamy. So PB, I think peanut butter, hopefully your peanut butter doesn't have lead in it, but it can hopefully help us remember that lead is PB. Another one that I've got a memory device for is SN. Tin, also a metal, often used in like roofing and coating nails, I think. Anyway, tin, is there a tool for tin that starts with SN? Tins, maybe it's just my brain. There's scissors, basically, for cutting tin snips. So the SN makes me think snips, tin snips. If those help you, awesome. If they don't, I'm sure that you can find other helpful tools from people online or make your own. All right, practice a few of these. If you've got your yellow sheet, that's a great reference to have. We want to find the name and the atomic number for each element. The atomic number, Z, is the number that shows up above the element. So for example, for nitrogen, the 7 that's in the top right corner or above, that's the atomic number, the number of protons. Initially, if you haven't spent much time looking at the periodic table, initially you will be quite slow navigating our 118 elements. As you get more practice, you'll get faster. You'll be like, oh, I remember that one shows up on this periodic table. You'll instantly jump to the right spot. Once you've worked with it enough, you just know where they are. Like you could probably, eventually you might get to the point, you give somebody a blank periodic table and they could fill in where some of these things are. I don't expect you to get there for this class. So let's find NA. Where is North America? Left side. First column, third row. So Na, what's its atomic number? Its atomic number, Z, is 11. And what is its name? Sodium. Now we're looking for Ni. Where do we find Ni? Yeah, first row in the middle and the 10th column. We've got Ni there. What's its number?
28.
It's 28. And what's its name?
Nickel.
It is nickel. Then we've got P. We can find P in the top right area of the periodic table. It's in column 15, third row. It's got the number 15, and it is phosphorus. And then we've got Ta, a very enticing element. Where is Ta? Yeah, it's the 5th column, 6th row, it looks like. Ta, it's number 73, and its name, tantalum. Questions about any of that? You could also, if you're bored or proactive about your studying your periodic table, you could play a game. You and another person just go back and forth. One of you picks a symbol, the other person tries to guess the name, and you just kind of have like a word hunt on your periodic table. Could be fun, could be a good studying method. So a little bit more history that's not in the slides. Z, the number, the atomic number, from German Zahl number, used to be like the position on the periodic table that they were in. So it wasn't laid out the way that we currently have it. The way it's currently laid out is thanks to Dmitri Mendeleev. Dmitri Mendeleev proposed the periodic law. He said if the elements are arranged in order of increasing relative mass, certain sets of properties will recur on a regular basis, which is the same as periodically. So the reason that it's called a periodic table is because it comes over a regular period. So just like a pendulum on a clock swinging, the time it takes for it to go through one full cycle, that's the period. It's the same for our periodic table of the elements. There are certain properties that occur again as we get through another row. So that's part of the reason that we've got it laid out the way that it is. That also means that there's extra information in there, and if we learn the tools, if we learn what that information is, then we can pull that out from the periodic table when we want to. So we will be learning some of that. Mendeleev's periodic law was based on observation. It was mostly true. Wasn't exactly true, just mostly true. Didn't give a reason for that observation. Only theories can do that. We will learn a little bit more about why those period properties recur. For now, we can learn some ways of breaking down the periodic table. So one pattern that we can find on the periodic table is we can break things on the periodic table down into 3 groups. We can break them down into metals, nonmetals, and semimetals, as we can see on our periodic table in the slides, right? Our metals exist primarily in this left and lower left side. Laser pointer, go. Other laser pointer, go. We did it. So most of the periodic table is metals. And a way that we can remember that that group is metals is there's things like Fe, iron, Cr, chromium, like chrome makes things shiny, titanium, gold, silver, stuff that we would probably identify as metals, all exists over in this big chunk of the periodic table. Even like Sn, tin, we would hopefully recognize as metal, and aluminum. Right, so we've got metals kind of all throughout. That can remind us those are the metals. And then for the nonmetals, that's this upper right corner, and hydrogen sort of also gets thrown in there. And then the semimetals, metalloids or semiconductors, also get thrown in on this little step line, the thick line that we've got on the periodic table in the class. So you should know those 3 kind of general zones as metals, nonmetals, and semimetals. So metals are most of the periodic table. They're basically the left side. They've got properties that we would hopefully identify as properties that metals have. They're good conductors of heat and electricity. That's why we make our wires out of copper. That's why you can buy fancy pans for cooking that are also made out of copper, and they're made of metals generally. You can also pound them into flat sheets to make roofing for a shed. You can pull them into wires to conduct electricity. They're often shiny. We like shiny, so we like gold, silver, because they are shiny and they stay shiny. Silver not as much. And they also tend to lose electrons when they undergo chemical changes. Metals lose electrons in chemical changes. That's arguably the most important part of this slide. They're the left side, and they also lose electrons. Our nonmetals, on the other hand, the upper right side of the periodic table, have more varied properties. Some of them are solids at room temperature. Many of them are gases. These tend to be poor conductors of heat and electricity. Also, they're gases, so they wouldn't conduct heat and electricity very well anyway. And they also tend to gain electrons when they undergo chemical changes. So nonmetals gain electrons in chemical changes. again, arguably the most important thing on this slide. Know where they are, they're the upper right side, and they gain electrons. If you gain an electron, what's the charge on an electron? Is it positive or negative? It's negative, so if you gain a negative charge, what's your charge? Negative. You've added a negative, so it's negative. More negative, because you added negative. So our nonmetals are going to tend to have negative charges when they gain electrons in chemical changes. And then our weird ones in the middle along that zigzag line, you also have that zigzag line on your yellow sheet. Some of those on that zigzag line are metalloids or semimetals. These tend to have more diverse properties. They're also called semiconductors sometimes because of their intermediate electrical conductivity, which can be used in making electronics, like silicon. Silicon is usually one of the backbones of electronic devices. If you're going to know one semimetal, one metalloid, one semiconductor, it should be silicon. Otherwise, we don't really deal much with metalloids. All right, let's classify each of these elements as a metal, nonmetal, or metalloid. First up, we have Se. Se we find on our periodic table. Any guesses on what Se might be? It's either a nonmetal or a metalloid. I think it does get classified as a nonmetal. But if you guessed metalloid, I think that would also be fair. Next up, we have Mg. Mg is over here. What do we think Mg is? Yeah, Mg, magnesium, is a metal, sometimes used in rims for cars, I think. And we also have Ge. What do we think Ge is? Yeah, it's a metalloid. Guessing a metal would also be fair. And then what about Ag? Metal. Yeah, Ag is silver. That's definitely a metal. I'm not going to give you probably, unless it's silicon, I'm probably not going to give you a metalloid on an exam for classifying elements. If I was going to give you one, it would be definitely one of the two spots where it's metals or nonmetals. Another way that we can split up our elements is into main group elements and transition elements. So our main groups are the first two columns, they have names, and the last 6 columns. This big block in the middle, those are the transition metals. Everything else is main group. And we don't really talk about lanthanides and actinides very much in the class. So main group, first 2 columns, last 6 columns, and that middle block, that rectangle in the middle, that's our transition metal or transition elements section. We love main group elements because they have very predictable properties. At this point in chemistry, we probably do not love transition elements. In chemistry, we love them for other reasons, but in chemistry, probably don't love them because their properties are kind of all over the place. They make things complicated. I took a course in grad school that was exclusively focused on transition metals. To give you an idea of how much there is to talk about, spent 10 weeks learning about it at UC Davis. It was an interesting class, not my favorite, but we've got stories from it. Each column we can call a family or a group of elements. So if you look at the periodic table that we have in the class, if you've got great eyes, you may notice that it says group over the very top left. Group or column or family is each of the vertical elements on the periodic table. Some of them have names. There's 4 that we want to know the names of. So these 4 that we're seeing here, those 4 groups we want to know the names of. The first one, our group 1A or 1, this A number here, that means main group. Anything that's got this A means that it's main group. If it's got a B, then that means it's going to be the transition metal elements, that transition block. The numbering is a little weird for that. I think this is mostly used in the US, the 1A, 2A, 3A. It goes up to 8A. So this 1A group is our alkali metals. So group 1, alkali metals, and these are very reactive metals. You can find videos of people putting these into water on YouTube. So they'll take lithium, sodium, potassium, they'll move their way down the bottom. They can't do francium because there's like 3 grams in the world. But the rest of them, you can get enough that you can throw a little pill-sized amount into some water, like sodium, potassium. They light on fire and they like dance around the surface of the water. For cesium, I think it explodes. So that's a fun one to look up. Very reactive metals, they just do that when you put them in water. Less reactive, and one group over, are the alkaline earth metals. So our group 2/2A is alkaline earth. Our second of 4 groups that you should know. Which number is bigger, 1 or 2? 2 is bigger than 1, great. Which name is longer, alkaline earth or alkali? Alkaline earth is longer, so alkaline earth comes after alkali metals. If you're having trouble remembering which one comes first, alkali comes first, it's shorter. Alkaline earth comes later because it's longer. As long as you remember the first 2 groups, though, that's probably most of the time decently okay. But we should know group 1, alkali, group 2, alkaline earth metals. Skipping over a bunch of our periodic table, going to the second to last column, we have the halogens. So 7A or 17 is the halogens, and these are very reactive nonmetals. There's a cool video, I think it's by the Royal Society of Chemistry. They take cesium. Cesium is that CS in the bottom left of the periodic table, our most reactive of the alkali metals, and they react it with fluorine. They prepare fluorine and they react fluorine and cesium together. Fluorine's the most reactive of the halogens, and it produces quite a fun reaction. It's like a 10-minute video. Good stuff from the Royal Society of Chemistry. It's also like 11 years old. And then moving over one column, we've got the noble gases. Noble gases are chemically inert, meaning they do not react. There's a fun trick that you can do with helium. If you get helium balloons, right, you take the helium balloon, you poke a little hole in it or you open it up, you breathe in a little bit of the helium, and then you start talking and your voice gets like Looney Tunes high, right, gets kind of squirrely, pitch shifts up. The reason that you can do that, and there's not a lot of negative side effects as long as you keep breathing air every now and then, is because it's a noble gas, so it doesn't really react with stuff. That's part of the reason that we use helium in our party balloons. Another option would be to use hydrogen in our party balloons. Hydrogen is not chemically inert. It's very flammable. So if your balloons got a little too close to the birthday cake, boom, big explosion. Much more surprising than just a balloon popping. Another fun trick, so helium's less dense than air. Argon is more dense than air. And so if you ever get your hands on some argon and you want to try this, I don't recommend it for legal reasons. But if you do want to try it, argon, since it's more dense there, if you breathe it in and you start talking, it pitch shifts your voice down. I'm sure you can find videos of people doing that on the internet. It's pretty fun. And since it's a noble gas, it's not really, shouldn't be bad for you, in theory. All right, which group or family, if we have a name as well, does each of these elements belong to? So finding some elements, we're going to put them in a group. It can be 1 through 18, 1A through 8A, etc. And we can also have a name for that family or group. So let's find Li. Li is in our far left column. So this is group 1/1A, and that is our alkali metals. AR, we just talked about this one. Right, AR is in our far right column. That's group 18/8A, and those are the noble gases. Where do we find Cl? Cl is right next to AR, so that's going to be group 17 or 7A, and those are the halogens. And then last we've got SR. Where do we find SR? Yeah, it's group 2. It's number 38. So that's group 2, and what's that group called? Yeah, that's our alkaline earth metals. Questions so far about our periodic table? I'd also like to mention at this point, at no point in the class will you be expected to have the periodic table memorized. Again, you do not have to memorize the periodic table. It's a waste of time. Thank you. So we've talked about changing the number of protons. What happens if you change the number of protons? Yeah, it'll turn into a different element. So the number of protons, that's that number in the top right, the Z, the atomic number. If you change that number, it turns into a different element. We're going to talk now about changing the number of electrons. If you change the number of electrons, we're making ions. So in chemical reactions, it's common for atoms to lose or gain electrons. What charge do electrons have? Negative charge. So it's common to gain or lose electrons which have negative charge. When that happens, we make charged particles, either positively charged if they gained electrons, or negatively charged, positively charged if they lose electrons, negatively charged if they gain electrons. And we call those ions. So ions are charged particles. We'll box that in. We've got two options for names. We've got cations. We've also got anions. Cations are positive charge. And this can be a little easier to remember if you intentionally misspell positive. So cations, cat ions, are positively charged because cats have paws. They're biscuit makers. So cats are positively charged. Anions are negatively charged. And I don't know that there's a good memory tool for this, but anions kind of looks like onions. And raw onions make you at least look sad. right? Because they make you cry. So that's a negative. Cooked onions, of course, delicious. We love cooked onions. But raw onions are lacrimators. They make you cry. When we write ions, we write the charge in the upper right corner of the symbol. So we're going to have our 1 or 2 letter code for our element. And then in the top right of that, we're going to put our charge. We are going to write the charge in a way that you are probably not going to always get correct. We're going to write the charge with the number first, and then the plus or minus after. There are instances where we'll put the plus or minus first, but typically when we're talking about charge, we put the number first and then the plus or minus after. And that way of writing it lets us know that we're talking about charge. Presumably that's the reason that we do it, or it's just convention. So for example, barium with a 2 positive charge, we use the symbol for barium and then the 2 plus in the upper right corner. Or we would call that superscripted. Phosphorus with a 3 negative charge, the little 3, and then the minus afterwards. Please try to get the correct order of number and positive or negative. Okay, we're going to talk about losing electrons first. What charge do electrons have? Negative. So if we lose negative, what charge are we going to have? We're going to have a positive charge. So in reactions, lithium atoms will lose 1 electron and they'll form lithium plus ions. So lithium, just starting off with atomic lithium, goes to lithium plus, and an electron also exists somewhere. That's just there to balance the books. The charge of an ion depends on how many electrons were gained or lost. We can calculate ion charge. The simplest way to do it, if we're going to do an equation, the simplest way to do it is number of protons minus number of electrons. So for lithium, Li+, it's got 3 protons, it's got 2 electrons. 3 protons minus 2 electrons gives us 1, and it's a positive 1, so our charge is 1+. So we don't have to do any flipping negatives if we calculate it this way. Another way, the way that my brain likes to do it, is I'd look at, okay, 3 protons, 2 electrons, which one do I have an excess of? We've got 1 extra proton. Protons are positively charged, so it's going to be a 1+ charge. If we gain electrons, like fluorine likes to gain 1 electron, and it becomes F-. I'll also point out here, omit a 1 in the charge. This is also convention. So if we've got +1, -1 for our charge, we just write plus or minus, rather than also including the 1. Again, our charge depends on how many electrons were gained or lost. So we're going to do number of protons minus number of electrons. We can figure out the number of protons from the periodic table. The atomic number in the top right corner and the top of the cell is 9. We said that we gained 1 electron, so 10 electrons. We have 1 excess of electrons. We've got more electrons, we've got 1 extra. Electrons are negatively charged, so our charge is 1-. That's the way that my brain does it. If that works for you, awesome. If not, then number of protons minus number of electrons might be your key, your ticket to success. Questions about our ions? All right, so we've talked about changing the number of protons. That changes our element. We've talked about now changing the number of electrons. That gives us ions. We're going to talk about our third subatomic particle, our neutron. If you change the number of neutrons, you get isotopes. Can somebody close the door? So isotopes are when we change the number of neutrons. Thank you for closing the door. So all atoms of a given element have the same number of protons because the protons defines the element. However, the number of neutrons can vary. So Dalton's original theory said that all atoms of the same element are going to have exactly the same mass and other properties that distinguish them from other elements. He was wrong. So point 2 from Dalton's theory that we looked at today was actually wrong. All atoms of the same element do not have the same mass because the number of neutrons can vary. And when we vary the number of neutrons, those are called isotopes, different versions of the same element. And in nature, these exist in normal natural abundances. So every element on the periodic table is going to have a unique percentage natural abundance of its different isotopes. And they can have 1 isotope, they could have 2 or 3 or 4, possibly even 5 or more isotopes, depending on the element. You don't have to have isotopes memorized. You need to know what they are. But for example, for carbon, I wouldn't ask you what are the isotopes of carbon and expect you to have that as an answer. So that's good for us. We'll look at hydrogen as an example of one type of isotope because it's got the simplest nucleus. So the nucleus, remember that's our little core here in the middle. That's where our protons and neutrons go. In regular hydrogen, these numbers we'll learn about soon. Regular hydrogen, we've got just 1 proton in the center. It also has a common name, protium for 1. Deuterium, deut for 2, has also 1 neutron in its nucleus. And then tritium, the tri for 3, we've got 3 particles in the nucleus. And these normally exist, these naturally exist. You can find them out in the wild. You can also make them in a lab. Other things have different numbers of elements. The way that we break down our isotope symbols is like this. So we've got our element symbol in like normal size text, and then before it, superscripted, raised, we've got our mass number. Who remembers what our mass number is? Either the letter or what goes into mass number. It's not Z. It's A. And what does that stand for? It is atomic weight, so the number of protons plus the number of neutrons. So the number of particles in that nucleus. So if we go back and look at our hydrogens, protium, we've got 1 thing in the nucleus. It's just a proton. For deuterium, we've got 2 things in there. So we've got that 2 in front. Tritium, we've got 3, so we put a 3 there. So that's the total count of particles. Our atomic number is our lower number, also in front, and that is Z. Conveniently, A comes before Z in the alphabet, so we put A above Z. And Z is just the number of protons. So when we're writing isotopes out this way, the element symbol and the atomic number, these 2 things are linked because the atomic number determines the element, which determines the element symbol. So those 2 things always go together. Another thing that I'd like to point out for our mass number and atomic number in these isotope symbols, the mass number is always going to be bigger or equal to the atomic number. The only time it'll be equal is here. This is the only time that it's equal, is in protium. Every other time, we're going to have big number over little number. So it's A to Z, A over Z, and it's also big number over little number. So we've got isotopes for neon as well. We've got 20 over 10 Ne, 21 over 10 Ne, 22 over 10 Ne, and those have different numbers of neutrons. Another fun thing that we can do is we can calculate the number of neutrons. And it's actually really easy if we've got things written out in this way, where we've got big number over little number. All we're going to do is subtraction. So if we add a little subtract sign in front and equals underneath, we've got 10 neutrons in that first isotope. The bottom number is the number of protons. The top number is protons plus neutrons. If we subtract the two, the protons cancel. We're left with the neutrons. That's a calculation that we'll sometimes want to do. Questions or confusions? Cool. If I'm going too fast, asking a question is a great way to slow me down. So I'm just throwing that out there. If you're confused, Mr. K, I'm confused. And then we'll figure out what you're confused about. So mass number A, we saw before, it's number of protons plus number of neutrons. And we can calculate the number of neutrons. Do A to Z, A minus Z, top number minus the bottom number, if we're using that particular isotope form. There are also other isotope symbols. So that's one of the ways that we can write isotopes. There's some other ways that we can write them as well. So this is the other ways to write them. We can use either the chemical symbol or the chemical name. So the 1 or 2 letter code or the full name. Follow it by a hyphen or a dash, whatever you want to do. And then the number of the isotope, the mass number of the isotope. So like hydrogen, deuterium, hydrogen with 1 proton would be hydrogen 2, or it would be H2. The reason that we're including the mass number is because the symbol and the bottom number are linked together. If you know one of them, you can figure out the other one. So we don't need to provide that lower number. We have to give that top number because that also has in it the number of neutrons. All right, I will give you some time to work on this. Next one. We're going to do this one together. So we want to know what are the atomic number, mass number, and symbols. Let's do all 3 of them for the bromine isotope with 46 neutrons. Great place to start here, bromine. We've got bromine. What's our symbol for bromine? It's Br. So we can find bromine on our periodic table. It's one of our halogens. So it's on the right side. The periodic table in the class has it in blue because it's a liquid at room temperature. So we've got bromine, and what's that number in the top right for bromine? It's got 35. And is that the atomic number or the mass number? It's the atomic number. So its atomic number is 35, and that's the number of protons. The mass number is the number of protons plus the number of neutrons. So our mass number, which is A, is going to be our 35 protons plus our 46 neutrons. That's going to give us 81. So we got a value for 81, and now we need to add in the 35 and the 81 in front of our BR. Which one do we put on top? We put the 81. Why do we put the 81 on top? Because that's the rule. It's the bigger number. It's the mass number. Any of those works. So we put the 81 on top, and the 35 goes down below. That's one of our symbols. That's our short symbol. What's one of the other ones? Yeah, we've also got Br-81. We've also got written out bromine-81. Questions? I'd also like to point out, you may know this already, chemistry is very pedantic. We care about all the little tiny details. One of the little tiny details that's often overlooked that I'd like to just mention here, notice that I wrote bromine with a lowercase b. Anytime that you're writing the name for an element, it should be lowercase unless it leads off a sentence. So this is just an aside. It's probably not something I'd mark you off points, but it just helps with us knowing how to write like chemists. Element names are not proper names. So don't capitalize them unless they lead off a sentence. Okay, apparently I searched for periods. I don't know if you can see that's highlighted. Yeah, you can. Apparently I searched for periods. Let's get rid of that. How many protons and neutrons are in this potassium isotope? I'll give you some time to work on this. You can consult with your neighbors or your notes, compare answers, duke it out, whatever you need to do. All right, what do we got for number of protons in this potassium isotope? It is 19. 19 protons, it's that lower number. We could also figure out that it's 19. If we remember on the periodic table, it's that number in the top right. So if we're not sure which one it is, we can always revert back to the periodic table, look for that top number. That'll be our atomic number, our number of protons. To figure out number of neutrons, what are we doing? We're subtracting. So we've got 40 over 19K. If we do a little subtraction, we get 21 neutrons. So that's a calculation. These are things that we should be able to pull out or put back in at will, and hopefully relatively quickly. We want to determine some ion charges based on numbers of protons and electrons. So we've got different elements. We've got cobalt, iodine, and nitrogen, and different numbers of electrons that we're told that those things have. So for the first one, cobalt, does anyone know the code for cobalt? Cobalt is CO. We can find CO. It's one of our transition metals. We find CO. Why is it important that we find CO? So we know the atomic number. So we find CO. It's got a number of 27. That 27 is the number of protons. If we can do a little bit of math in our heads, all right, we've got 27 protons, 25 electrons. Which one do we have more of? We've got more protons. How many more protons? we've got 2 extra protons. And protons are what charge? Positive. So this is going to be CO2+. So this is like the what my brain is thinking. More protons, we've got 2 extra, they're positive, so it's a 2+. Alternatively, we can do protons minus electrons. This is the formula that we had in the slides. So we do 27 minus 25. We get a positive 2, so that means 2+. For iodine, we find iodine on the periodic table. It is number 53. It's one of our halogens. So I has 53 protons. So we can do 53 minus the number of electrons, and we get what? -1. So it's a 1 minus charge. That's going to be I minus. And then last but not least, we have nitrogen. Nitrogen is N on the periodic table. We find it in the upper right-hand side of the periodic table. So N has 7 protons, 10 electrons, 7 protons. We've got 3 extra electrons. 3 extra electrons. Electrons have negative charge. So it's N3 minus. All right, last one. Let's find the number of protons and electrons in the S2 minus ion. So working the other direction, starting with the symbol, going back to numbers. So we're going to have to find S on a periodic table. S is in the top right section. It's also a nonmetal, sulfur. It's got the number 16. What does the 16 mean? So it has 16 protons. 2 approaches to figuring out how many electrons it has. One of the approaches is we use that formula. So that formula is charge equals protons minus electrons. We have the charge, it's 2 minus. We have the number of protons, it's 16. So 2 minus, we'll write it as -2 for now. It should be 2 minus, but we'll write it that way. Equals 16 minus the electrons. And now we get to do some algebra. So to get the electrons by itself, to get the the 2 moved over, we're going to add E to both sides. So electrons minus 2 equals 16. We add the 2 to both sides. Electrons equals 18. The other solve, which I think is potentially easier, we've got a negative charge. The negative charge means we have extra electrons. It's got a magnitude of 2, so we've got 2 extra electrons. So we take the number of protons and we add 2 to it. We must have 18 electrons. That would be the other solve. Questions at all? Okay, then we'll stop there.